Welcome to Essential Problems with CRIP. This video will focus on helping to understand the periodic trends, focusing primarily on electron affinity and ionization energy. So let's begin. First, let's make things simpler. So here we have S block, P block, right? S block, P block, D block, and F block. You will not be required to explain periodic trends in either the D block or the F block. This is because there are many exceptions to the general trends that we really need to get a hold of, and that's beyond the scope of this course. So we will be required to explain the S and the P block trends, and those are pretty much what we call the representative elements. So let's focus on also where we see deviations from the fact that as we go across a period, the ionization energy and the electron affinity should just generally increase. Generally, because as we go across a period, right, we will be increasing number of protons, and therefore attraction, electrostatic attraction, will increase across a period. So there's going to be noticeable drops in certain areas. So for instance, if we take group 18, so if we take neon here, the electron affinity will drop in group 18. And it's very clear as to why, because this is when all the electrons are filled in a given energy level, and an electron must exist in a new energy level. So the affinity for that electron will drop substantially because of it. So group 18 will have incredibly low electron affinity. And so notice argon here, that new electron must exist in the fourth energy level. For krypton, new energy level must be occupied if an electron is to be added. Same thing for xenon in the sixth energy level, radon in the seventh energy level, and oganesson in the eighth energy level, which isn't even shown here. So that would be the first main trend. Another trend would be associated with group 2. And the electron affinities for group 2, and we should really start with beryllium, it will drop because we're starting a new sublevel. So notice here, if we were to add an electron to beryllium, it would have to exist in the 2p sublevel. For magnesium, it would have to exist in the 3p sublevel. For calcium, it would have to exist in the 3d sublevel, but still a new sublevel. For strontium, it would have to exist again in the 4d sublevel, and so on. It would have to go into 4f, and radium as well, into 5f. So again, you would have to go to a new sublevel, and therefore the electron affinity would drop for group 2. And there's one more other place where electron affinity would drop, and that would be in group 15. And this is because we're at a half-filled sublevel in which every orbital is singly filled. And so that's when pairing is to begin. And so if I were to add one more electron, it would have to exist in the paired state. So notice for phosphorus, same here. For arsenic, again, antimony, bismuth, and moscovium, they would all have to begin pairing, right, if another electron were to be added. And so we can also see this represented in the data. So if I may, I'm going to scroll right up here, and we'll go to properties. So let's see, if we look carefully here, and let's click on, actually we will click on fluorine first to illustrate the example. Notice here, electron affinity, 328 kilojoules per mole. And if we click on neon, the electron affinity is nil. Again, for chlorine, 349, and click on argon, nil. You could see the same effect over here if we go to lithium. Notice electron for affinity for lithium is still substantial, right? But for beryllium, 0. For sodium, substantial still, and then drops again. Of course, we can see if we were to just compare it, lithium, right, the substantial, beryllium drops, but then boron picks up again. And again, carbon increases, right? But then, of course, from what we were discussing, it will drop in with nitrogen. So notice electron affinity drops here, 7 again, because to add an electron to nitrogen, it would have to exist in the paired state. And then it picks up again with oxygen to fluorine, of course, then it drops with neon again. So here we can clearly see, based upon the data, that electron affinity is distinctly affected, right? As we go across the period, there is the general effect, right, of increasing electron affinity, but we must note these specific places where they will drop. So with that in mind, we can also address ionization energy. So let's go back to our chart here. So ionization energy will not drop at group 18, but it will drop at the group after that. It will drop in group 1. So it drops here because we have started a new energy level. So it's useful to focus on lithium here. And so because we've filled the first energy level and we're starting the second energy level. And here, sodium, we filled the second energy level, we're starting the third energy level. And here's the lone electron in the third energy level. For potassium, again, we're starting the fourth energy level. For rubidium and cesium and francium, again, starting this new energy level. That electron is very weakly attracted to the nucleus, and it's very easy to remove because of that. So that would be associated with starting a new energy level. We can look at group 13 and we see a similar effect, again, not as intense, but still significant, with starting a new sublevel. So notice as we start the new sublevel, the 2p sublevel, that electron in that new sublevel will be not as attracted as the previous sublevel. So it'll be more easy to remove. And we can see in each case we have a lone electron in a new sublevel. Finally, the last place where ionization energy will drop is in group 16, in which we have begun to pair within a given sublevel. And so that electron, that newly paired electron, will be quite easy to remove. And so notice oxygen, sulfur, selenium, tellurium, polonium, livermorium. There's one lone electron that has begun pairing in a given orbital, and it is easy to remove that. And so we can see how that's also supported by the evidence. So if we pull up properties again, and we can see first ionization energy right here. And if we say again, begin with lithium, notice the first ionization energy is there. But if we compare it to the one previous, right, helium's first ionization energy is insanely greater. So it drops substantially with lithium. It's still there, but it's incredibly smaller than the others. Now, of course, as we go across the period, it will increase, right? But we must note the drops. And so the drop occurs in 1 and 13. So notice the drop. But then again, as we increase and increase again, but it will drop in group 16. So there it drops slightly, but then it will increase again and continue to increase. Again, note a lot of students confuse group 18. It requires the highest energy to remove that electron. Again, we're talking about removing an electron, not adding an electron. So noble gases have an incredible attraction to their electrons. So, and you can see if we take another example, so continue on to sodium, notice we have the substantial drop, then picks up again with magnesium, again another drop with aluminum, then again increases silicon, phosphorus, sulfur, we're going to expect a small drop, and there's that little drop, and then chlorine increases again, and then argon the greatest. Finally, we can address the radii, the atomic radii on the periodic table. But of course, this is simpler because there really are only three main trends. So if we're focusing on the radius right here, we can see hydrogen, right? And then as we go across the period, the number of protons increases, the attraction increases, and the electrons are drawn closer to the nucleus, right? And we can see again with lithium, it gets larger because we started a new energy level, but then as we go across the period, it gets smaller and smaller and smaller and smaller and smaller until we start a new energy level again, and then it gets larger again. And then as we add more protons, more electrostatic attraction, the atomic radii gets smaller and smaller and smaller. And of course, there's one other trend here, which is as we go down a group, we see larger and larger radii in general because there are more shells. So here, notice helium was incredibly small, but as we go down that group, we see its size significantly increase. So that's all the trends that we need to really focus on. And till next time, Crip.